Hi everyone, I'm Mohammed and today I'm going to present our work securing Node-RED applications in collaboration with a fantastic team, Musard, Daniel, Eric, and Andre. Trigger action platforms seamlessly connect otherwise unconnected devices and services. Upon a trigger, the app in the platform performs a specified action in response. For example, getting an email when your camera senses motion, or saving new Instagram photos to your Dropbox. These platforms and apps manage users' digital lives by connecting various devices such as smartphones and cars, smart homes, online services, and social networks. Node-RED is one of the popular trigger action platforms. Here are a couple of real-world Node-RED apps. An app or a flow consists of a set of nodes linked together. In this example, once a new tweet is posted, if it's a positive tweet based on the sentiment analysis, it sends the tweet to the user. Another example is the earthquake monitor that prints an alarm to the user when there is a recent quake higher than a specific magnitude. The other one is a more complex flow, which is called the water utility for SCADA systems, monitoring the state of two water tanks and checks whether any of the pumps need to be started or stopped. Node-RED is indeed one of the popular JavaScript-driven TAPs. It's open source and can be run on your local machine, on a device, or in the cloud. The NPM stats say so far it has been downloaded more than 5 million times. TAPs in general, and Node-RED as an instance, use access delegation tokens, meaning that they act on behalf of the users, which also known as person in the middle. Node-RED uses the approach of end-user programming that any user can create and publish nodes and flows without being reviewed or any restrictions. So most of the Node-RED apps are indeed developed by third parties. And here it comes. They can be malicious. So our threat model in this paper is considering app makers being malicious. Generally, a collection of apps known as flows linking components called nodes, which can be run simultaneously. And here's the Node-RED architecture. A node is a reactive Node.js app triggered by receiving a message or time. Internode and interflow communications happen via direct message, passing through the wiring between nodes, and shared context at the level of flows or global. We have found severe vulnerabilities in the real-world dataset of Node-RED flows and nodes. A malicious node may abuse Node.js module like powerful child process to run an arbitrary code which can be even destroy the server. It's also possible to modify the red object, which is the main message passing object in Node-RED. A malicious node maker can abort the server by just this one line of code. At the level of users' data, for example, a malicious email node can change the source code so that the attacker receives a copy of every single email that the victim sends to anyone by just adding his email address in the node's source code, which is not visible for the end user in Node-RED, unless they investigate the node's source code in the server's directories. Our empirical study shows that more than 70% of existing Node-RED flows may violate users' privacy and integrity. As mentioned earlier, internode communications also can get attacked. In the water utility example, a malicious node installed by the user could modify the context variable relating to the tank's state to either exhaust the water flow or never start, or cause physical damage through continuous pumping or never stop. Context can be also used for sharing resources, such as Node.js libraries. An attacker can encapsulate the library such that it collects any sensitive information sent to the library. Our empirical study shows that around 20% of the flows make use of contexts, meaning that they can be targeted by an attacker. Here is a schematic diagram illustrating discovered Node-RED breakouts. A malicious app maker can compromise, trigger, and action data of other apps of the same user and the TAP itself by just developing a node installed by the victim. As the flows are visible to the end users in the graphical user interface, we can interpret them as security policies, unscented by the user. So information may flow between nodes only if it goes through the wiring, the visible links. In the earthquake example, the graph demonstrates a flow that retrieves earthquake data for logging and notifying the user whenever the magnitude exceeds a threshold. So, tampering of recent quakes node by other flows or nodes is prohibited, and no data outside of the flow should be accessible. Then we continue with our main research question: how to secure JavaScript apps on Node-RED? The answer is by node sandboxing or access control based on the least privilege principle. The challenge is that Node-RED apps require access node modules for their functionalities, while a malicious node might require additional modules for their evil intentions. For example, child process shouldn't be accessible for any nodes by default. It means we need access control at the level of modules and shared context. Sensitive values can be leaked to the outside world if we do not monitor the APIs and their values at runtime. So we need a fine-grained access control monitor at the level of APIs and their values. This motivates the need for a secure yet flexible way to integrate third-party apps, where Sandtrap enters. Sandtrap, which we introduced in Usenix 21, enforces four main policies: read, write, call, and construct. It's actually a novel JavaScript monitor that securely combines the Node.js VM module with fully structural proxy-based two-sided membranes to enforce fine-grained access control policies. The two-way policies allow the host and the sandbox to be protected from each other, mutually recursive. Other existing JavaScript monitors don't support for fine-grained controls of shared entities. On the other hand, Sandtrap allows the user to introduce policies at the desired levels: module, API, value, and context. We have instantiated Sandtrap for Node-RED and showed that the mentioned attacks are now prevented by the policies coming from the graphical flows. By default, and as a baseline policy, Sandtrap doesn't permit any node modifying the red object or using any modules than explicitly stated in the node's policy. We also prevented the attacks to shared context, such as the one explained in the water utility example. Our goal in this paper is also to formalize a core of JavaScript underpinning the Node-RED's programming model and the Sandtrap monitor to prove soundness and transparency. We have seen some of the security policies in Node-RED. For example, only me@user.com is permitted for the email node, or only nodes in water utility can write to the shared variable tank level. In our model, we define a node configuration along with its policy as a tuple including the program configuration, the array of successor nodes in the flow ID that the node belongs to, and the policies. P stands for API policy, specifying the list of permitted API calls. V denotes which values are allowed for an API. And S indicates whether this node can read or write to a flow or global context variable. So we define the command evaluation relation as a relation between configurations. We model Sandtrap node-RED using a small step semantics for command evaluation. As stated before, policies are in node configurations, and here are the enforcement rules for call, read, and write. Before evaluating an API call, Sandtrap checks whether the API and its values comply with the node policy or not. We use a big step semantics for expression evaluation. Reading variable or writing to a variable must be according to the node's policy, otherwise rejected. In the email example, the email node permits sendMail function to be called, but only with user-defined values, not the attacker's email address. In the water utility example, the pair tank level and read exist in the policy of the nodes that they may read the tank state. And the pair of tank level and write is also present in the nodes may write to the shared variable tank level. Other nodes can't read or write to the shared variable. We prove soundness and transparency of Sandtrap node-RED. Soundness theorem states that the monitoring at the level of nodes enforces global security, meaning that any execution under the monitor enforcing the node policies are secure. G here denotes the global configuration of the system, and V is the set of initial values. Transparency theorem says that the monitor doesn't modify secure execution, and it only raises an error if it observes a policy violation. It also states that the longest secure prefix of a given trace is preserved, which means that if the trace is secure, then Sandtrap accepts the whole, and if it's insecure, it truncates the execution by observing the insecure event. To sum up, in this paper, we investigated the security problems of node-RED and presents how an instantiation of the Sandtrap monitor secures node-RED apps. Fine-grained policies at the level of modules, APIs, values, and contexts are enforced by Sandtrap node-RED. We also introduced a formal framework for a core language JavaScript, modeling the essence of node-RED and suitable for reasoning about nodes and flows. We also proved that Sandtrap node-RED guarantees the soundness and transparency theorems. For further reading, here is the link to our paper and the Usenix paper, which explains more about Sandtrap in practice and how it applied for popular JavaScript-driven TAPs. Thank you for your attention, and I'd be eager to discuss more about our work.